In this video, we're going to start to talk about some, in the very broadest sense, the units that sort of make up a computer. So it depends sort of on how you decide to count. You might group some of them. And so some people will say anywhere between sort of 3 and 5. So if we're going with 5, it's the arithmetic logic unit, or ALU, or sometimes called the data path. Control, which is the ROM, the read-only memory. The memory, which is random access memory, RAM, and input and output. So ALU, control, memory, input, output, that's 5. Some people will combine the ALU and control to make the CPU, the central processing unit, and some people will sort of combine I and input and output and refer to it as IO. And so you can already see that like this is acronyms all over the place, CPU and ALU, and just more to come. So computer architecture is a lot of vocabulary, and a lot of the vocabulary is acronyms. Just have to get used to it. So a lot of what we do in computing is move things around. You're like taking instruction or data and taking it from this place to that place, but you finally get to a place where you're going to actually perform an instruction and take some pieces of data and somehow use it to generate a new piece of data. And that sort of get new things from old things. That usually happens in the ALU, the arithmetic logic unit. And it's made up of logic gates. Most of the computers made from transistors, and the transistors that sort of perform logic, that do combine zeros and ones, the numbers in the computer, to other combinations of zeros and ones. These are known as logic gates. And if we're doing something where the output ones and zeros depend solely on the input ones and zeros, and not on something we've done before, but just the things we're doing like right now, then this logic is known as combinatorial. And so everything sort of comes down in the ALU to logic. Arithmetic is really just, a variation on logic. And so we have these basic logic gates or operators. And so a logic gate is just like an electronic realization of a Boolean operator, sort of where sort of some sort of like high voltage, not that high, but relatively high voltage, or the existence of a current may be taken to be true and its absence, or low voltage false. And then we can have some circuit that combines them in some way that corresponds to logic. And we have our basic gates are and, or, not, NAND, and NOR. So if we have two or more Boolean expressions, things that are true or false, and we AND them, then all of the input things had to be true to get out a true. Otherwise, we get a false if we have an AND gate. An OR gate, if any one of the inputs is true, you get a true. Or you could say it the other way around. You could say they all have to be false to get a false with the OR. A NOT takes in a single input and just gives you the opposite. So if you gave it a true, it gives you a false, and vice versa. A NAND is, in some sense, electronically more fundamental, but logically, it's just, perform an and then once you get the result of the and, sort of apply a NOT to it, or invert it. And similarly, a NOR is take an OR operation and follow it by a NOT. So again, to some extent, they are more fundamental. NAND and NOR are sort of more fundamental electronically, but logically, we can think of them as a combination of and NOT, or and NOT. So we said that if the logic that we have happening is all all determined by the inputs and nothing that might have happened previously, it was combinatorial. But some things are depend on sort of like what we've done in the past, that we reach some state and then we have these inputs and then some combination of the state and the inputs that will determine our output. And such logic is called sequential. And so we need some way in a case like that to sort of like hold on to our state. And this is where uh, registers come in. So basically, overall, it's the logic is sequential. It depends not just on the input, but also on the state. The state is held by something that can sort of hold on to the values that we've developed so far. These are often going by the term of register. There are like all sorts of special purpose registers. The register sort of most closely associated with the ALU we talked about before, sometimes known as an accumulator. And these registers that are like in the CPU and working with the ALU, they are sort of like as you do calculations and logic, they're sort of the computer's like scrap paper if we are you know pretending the computer is a person and needs a little bit of paper to write down a sort of partial answer along the way. If we're talking about these things that hold one's state to sort of remember a high or a low or a combination of highs and lows, um, we're working with bits. And so if we go focus down to the case of a single bit and holding on to the state of a single bit, then the circuit is known as a flip-flop. If we are just holding on to a sequence of them, then we call that a register. Sometimes we add a little bit of functionality to a register and give it a special purpose. So if we allow a register to give it the capability of like basically adding one to itself, then we have a counter. Or if we give the register the ability to move all the ones and zeros like to the right or to the left, then we have a shift register. And if we put a bunch of registers together and and give ourselves the ability to pick one, to address, to select out one particular register, then we have what we generically call, what we typically would call in a computer, its memory, or RAM, random access memory. The other part, so that was the ALU, the thing that changed the data, was the ALU, but the other part of the CPU, the central processing unit, was the control. So every little piece of hardware in the computer needs some sort of like control input. It can do its thing or maybe a set of things, but it needs to be told to do it. And that is the purpose of control, to tell all the little hardware devices that make up the computer, do your thing or don't do your thing. Do it now, or of the five things you can do the third one. This is the job of control. So it doesn't change the data, but it controls the things that change the data. It controls the moving around of the data. It controls what the ALU is going to do to the data, and so forth. So again, everything has the hardware's dumb. It does only, it can do only what it can do. Registers hold values, or you can sort of maybe clear them, or counters can hold their value, or they can increment. And then they will have this like active input, this like do you do your thing or don't do your thing. And so that is where the control comes in. Control will have access to the active input of all little devices and make them sort of wait around or do their thing. And that, depending on the way the electronics works, we're usually working with binary. So there are different ways you can work with something. You can make something happen when you put in a high. You can make something work when you put in a low. And so you can talk about something being active high or active low. And in some cases in memory, you do it when it changes sort of from high to low or something like that. The control that we talked about is ROM. We make a distinction in memory typically between RAM and ROM, and the control is ROM. So I can rearrange data and instructions, and that's what makes the computer programmable. That I'm changing what in the order of instructions. It has a set of instructions it knows how to do, but I can rearrange them and I can give it different data for those instructions to act on, and that is programming. And so that's the part I can change, but there's a part that I don't change. I either don't change or I change quite rarely, and so I put those things in read-only memory. So I'm not going to change it. Like I'm going to change the order of I'm going to change the data. I'm going to change the order of the instructions. But once I have an instruction, it's got to be performed a certain way. And so that information of how to perform that certain instruction in that certain way, that's going to be put in ROM, because that's either not going to change or change quite rarely. Okay. On the other hand, the memory that we talked about, that is the thing that we expect. That's the part that we expect to change. So we will put our program, our arrangement of the instructions. So the computer it has certain things it does, we rearrange them. So we expect that rearranged sequence of things we want to do to be in the memory. We want the data that it's acting on to be in memory. So this is the part of we're holding on to something, but more temporarily. And we put those things that we expect to change from scenario to scenario, or even within the course of the program. We put those things in memory, and that's random access memory, or RAM. So RAM is this addressable set of locations. So we talked about a register as something that just holds a sequence of ones and zeros, but then we have sort of a set of these registers, and we figure out a way to identify each one, and we call that addressing. We address them. And so if you supply the address, then you have access to that value. And that's what we mean by random access. Then, like at random, I could supply you any address and get the value at that address. Now, it might not be random as far as the programmer is concerned. The programmer wants to do a certain thing, and in the programmer's mind, it's by no means random. But in terms of like the hardware, it can be any address. So it can be any random address as far as this RAM is concerned. Yeah. So that's what we mean by the random access: supply the address and get the value at that address. But another distinction in between random access is as opposed to sequential access. So if you have a way of storing ones and zeros, and your access is as the following: that everything is in a particular order, and you can't jump around. You've got to go from 1 to 2 to 3. You've got to go in this sequential order to get at whatever it is you're trying to get at. And so a classic example of this would be like an old way of to watch a movie would be on a VCR tape. So the information to show you the movie is in an order. And if you liked something in the middle of the movie, you like somebody's quote in the middle of the movie, and you wanted to see that, but the tape was at the beginning of the movie, then you're going to have to move through the whole sequence. Even if that is fast forwarding, you still have to go through it. So that is sequential versus random. You can sort of pick the place and go to it. So, like if you're watching a movie on a DVD, then that's more random access. You can, if you understand the spot you want to jump to, you can jump to it relatively quickly. Um, Now, it's important to understand the difference between memory and storage. Memory is something that you need to have a computer because you want the computer to be programmable. You want to be able to change the order of the instructions, the data it's working on, and you do that by having memory. So, memory is an essential unit of the computer. If you want to store your things for a longer time, then you will put them in storage. This In our units that we talked about, storage is really part of I/O. You don't absolutely need it. You need I/O. There's no sense, and you can't. If you can't put anything into the computer, it's no use to you. If you can't get anything out of it, it's no use to you. But strictly speaking, you don't have to be able to store anything. So earliest computers don't have storage, but it's very useful. So we have it in the long run. And typically, one of the distinctions between memory and storage is memory tends to be what we call volatile. So we need power. If we have that power, those ones and zeros are sort of held. But if the power goes out, we lose that information, whereas storage is non-volatile. It will hold on to things longer. It's a much longer term holding on and doesn't require power to do the holding on. And then finally, we have, just to have all the units of the computer, we have I/O. We need to be able to get things in. We need to be able to get things out. We have keyboards and microphones and things like that for getting information out. We have uh, LEDs. We have just for little displays of little things being on and off. We have computer screens. We may have speakers, so we have output. And and again, the our main storage device, like a hard drive, really in this very basic unit way of thinking of things, are really part of I/O. Okay, that's it for this one. Thanks for your attention.